Hello there, and welcome to Science for Sleep, the quiet corner where curiosity slows down, explanations take their time, and the universe becomes a gentle place to wander through at the end of the day. I'm glad you're here. Settle in however you're comfortable, let your shoulders drop a little, and allow your thoughts to loosen their grip for a while. There's nowhere to rush, nothing to solve, nothing you need to remember. Just listen and drift along with the story. Tonight, we're going to explore a question that stretches far beyond human history, beyond civilizations, beyond even the age of our own world. We're going to ask a very simple question, one that sounds almost childlike when spoken aloud, yet opens a door into billions of years of cosmic history. What is the oldest planet in the Milky Way? It's a curious thought, isn't it? Somewhere out there, orbiting a distant star, there may be a world so ancient that it formed when our galaxy itself was still young. A world that existed long before the Earth cooled, long before the Sun ignited in its present form, long before the continents, the oceans, the forests, or any creature that ever walked or swam or breathed here. Imagine a planet that has been circling its star for longer than complex life has existed anywhere in our galaxy. A place that has watched stars come and go. Supernovae flash and fade, clusters drift, and galaxies slowly reshape themselves over immense spans of time. A world that has simply endured. When we think about planets, we often picture places like Earth, Mars, or perhaps distant exoplanets discovered in recent years. We imagine landscapes, atmospheres, maybe oceans, maybe ice. But we rarely stop to consider how old such places might be, not just in millions of years, but in billions upon billions of years. Time on that scale becomes difficult to grasp. It slips through the mind like sand through open fingers. And yet those immense spans of time are very real. The Milky Way itself is more than 13 billion years old. Our Sun is about 4.6 billion years old. Earth formed shortly after that. But planets did not begin forming only when our Sun was born. Some formed far earlier, in regions of the galaxy that were already rich with the materials needed to build worlds. Which leads us gently to tonight's journey. But before we go any farther, let me ask you something simple. Where are you listening from right now? You don't have to answer out loud, of course. Just notice it for a moment. Perhaps you're in bed, or on a sofa, or sitting quietly with headphones as the day winds down. Maybe it's late evening where you are, or the early hours of morning. Perhaps the room is dim, and the sounds of the world outside have softened into the background. And what time is it for you right now? It's a fitting question, considering that tonight's story is really about time, though on a scale so vast that hours and minutes hardly matter at all. Still, each of us experiences time in our own small personal way, measured in breaths, heartbeats, and quiet moments like this one. If you find this gentle exploration soothing, or simply a pleasant way to let your mind slow down, I'd be very grateful if you gave the video a like and perhaps subscribe to the channel. It helps this calm little space reach others who might be looking for something quiet to listen to at the end of a long day. Now then, let's begin our journey. To understand what the oldest planet might be, we first need to step back and think about something deceptively simple. What it actually means for a planet to be old. Age, after all, is a relative thing. A mountain may seem ancient compared to a tree. A continent ancient compared to a mountain. But in astronomy, even continents are fleeting, temporary features that come and go in the blink of a cosmic eye. A planet's age is usually measured by the age of the star system in which it formed. When a star is born, a disk of gas and dust often forms around it. Within that disk, grains collide, stick together, and gradually build into larger and larger bodies. Over time, those bodies become planetesimals, then protoplanets, and eventually full planets. So when we say a planet is old, we really mean that the system it belongs to formed a very long time ago, near the beginning of the galaxy's history. But that raises another question, one that astronomers wrestled with for many years. Were planets even able to form in the early universe? At first, scientists suspected the answer might be no. The earliest stars formed from hydrogen and helium, the simplest elements, created in the Big Bang. Heavier elements like carbon, oxygen, silicon, and iron, the materials that make up rocky planets, were forged later, inside stars and scattered into space when those stars died. In other words, the universe had to go through generations of stars before enough heavy elements existed to build planets like Earth. This process takes time, enormous amounts of time. The first stars lived fast and died young, exploding as supernovae and enriching their surroundings with heavier elements. New stars formed from that enriched material. Then those stars lived and died, contributing even more elements to the galactic environment. Gradually, the raw ingredients for planets accumulated. It's a bit like baking in a way. You cannot make a cake until you have flour, sugar, eggs, and butter. The early universe had only the simplest ingredients. The more complex ones had to be created first, inside stars and released back into space. So for a long time, astronomers assumed that planets must be relatively late arrivals in cosmic history. But the universe has a habit of surprising us. As detection methods improved and telescopes grew more sensitive, astronomers began discovering planets in places they had never expected to find them. Some were orbiting very old stars, stars that formed when the galaxy was still young, and that suggested something remarkable. Planet formation may have begun earlier than anyone once thought. In fact, some of the oldest known planets formed billions of years before Earth even existed. Just pause for a moment and let that sink in. There are worlds out there that were already ancient when our sun was born. Worlds that had already completed countless orbits, while the cloud of gas that would become our solar system was still drifting, unformed, in interstellar space. It's a humbling thought. Here on Earth, we often measure age in human terms. A century feels long, 1,000 years feels ancient. But in the language of the cosmos, those spans are barely measurable at all. Even the entire history of human civilization occupies only the thinnest sliver of time compared to the age of some stars and planets. And yet those ancient worlds exist, silent and distant, orbiting their stars in the darkness. How do we find them? That question leads us into one of the most fascinating detective stories in modern astronomy. Detecting planets around other stars is not easy. Planets are small, dark, and lost in the glare of the stars they orbit. For a long time, astronomers had no way to detect them at all. It was only in the late 20th century that the first confirmed exoplanets were discovered. One of the earliest methods used was called the radial velocity technique. By observing the subtle wobble of a star, astronomers could infer the presence of a planet tugging on it gravitationally. Another method, the transit technique, involves watching for tiny dips in a star's brightness as a planet passes in front of it. Using these and other techniques, thousands of planets have now been discovered in our galaxy. Some are larger than Jupiter, others are smaller than Earth. Some orbit scorchingly close to their stars, completing an orbit in days. Others travel in wide, cold paths that take decades or centuries to complete. Among these discoveries are planets orbiting very old stars. And by studying the properties of those stars, their composition, temperature, luminosity, and motion through the galaxy, astronomers can estimate their ages. That's how we begin to identify the oldest planetary systems. But age alone does not tell the whole story. The environment in which a planet forms also matters. Some of the oldest stars in the Milky Way are found in globular clusters, dense spherical groups of stars that orbit the galaxy's core. These clusters are relics of the early galaxy, containing stars that formed more than 10 or even 12 billion years ago. Imagine a night sky from a planet in such a cluster. Instead of a handful of bright stars scattered across darkness, the sky might be crowded with thousands of stars, shining so brightly that true night never fully arrives. It would be a very different kind of world, and somewhere in one of those ancient clusters, astronomers have found something extraordinary. A planet so old that it challenges our understanding of when planets first began to form. We'll come to that remarkable discovery soon, because its story is worth taking slowly. For now, it helps to reflect on how vast the timescales involved really are. The Milky Way has been forming stars for more than 13 billion years. Our Sun formed relatively late in that history. Earth, in a sense, is a latecomer to the cosmic stage. There may be planets that have existed for twice as long as our own world. What would such a planet be like after billions upon billions of years? Would its surface be worn smooth by eons of impacts and erosion? Would its atmosphere have changed many times? Would its star have evolved, growing brighter or dimmer over time? Planets are not static things. They change, sometimes slowly, sometimes dramatically. Mountains rise and fall. Atmospheres thicken or vanish. Oceans appear and disappear. Magnetic fields strengthen and weaken. Given enough time, almost everything changes, and yet the orbit of a planet around its star can remain astonishingly stable, continuing for billions of years, like a steady rhythm that never quite stops. That steady, patient motion is one of the quiet wonders of the universe. A planet does not hurry. It does not rush toward tomorrow. It simply continues, orbit after orbit, year after year, age after age. Now, before we can truly appreciate the idea of the oldest planet in the Milky Way, it helps to pause and think carefully about what the word oldest actually means when we're talking about the universe. It sounds simple at first. Something old is something that has existed for a long time, but in astronomy, that definition begins to stretch in interesting ways, because time itself operates on scales so large that our everyday sense of age becomes almost meaningless. Here on Earth, we measure age in ways that feel intuitive. A tree might be 100 years old, a historic building might be 500, a fossil might be tens of millions of years old, and that already feels enormous. When you hear that dinosaurs lived more than 60 million years ago, it can be difficult to picture. The number is so large that the mind doesn't really grasp it in a concrete way. It becomes more like a symbol than an experience. But astronomy moves far beyond even that. The Earth itself is about 4.5 billion years old. That's 4,500 million years. And even that, immense as it sounds, is only about 1/3 the age of the Milky Way galaxy. The galaxy began forming more than 13 billion years ago, not long after the universe itself came into existence. So when astronomers talk about the oldest planets, they're not speaking about differences of a few million years or even a few 100 million. They're often talking about differences of billions of years, spans of time so vast that entire planetary systems can form, evolve, and change dramatically within them. To understand this more clearly, it helps to think of the history of the universe as a kind of timeline, but one so long that the entire history of humanity would occupy only the thinnest line near the very end. If the age of the universe were compressed into a single year, human civilization would appear only in the last few seconds before midnight on December 31st. Planets, stars, and galaxies have been evolving for almost the entire duration of that cosmic year. So when we ask which planet is the oldest, what we really mean is this. Which known planet formed earliest in the history of our galaxy and has survived until now? That definition matters because planets do not form in isolation. They form alongside stars from clouds of gas and dust that collapse under gravity. The age of a planet is therefore closely tied to the age of its parent star, or sometimes to the age of the stellar environment in which it formed. Astronomers cannot usually pick up a planet, examine it directly, and determine its age the way a geologist might date a rock. Instead, they look at the star the planet orbits. By understanding the star's composition, temperature, brightness, and motion, they can estimate when that star formed, and if the planet formed along with it, that gives a reasonable estimate of the planet's age as well. This process involves a great deal of careful measurement and modelling. stars change over time in predictable ways. Their brightness shifts, their chemical composition evolves, and their internal processes gradually alter their structure. By comparing a star's observed properties with theoretical models, astronomers can estimate how long it has been shining. It's a bit like examining a candle and judging how long it has been burning by the length of the wax that remains, the size of the flame, and the way the wick has changed. Of course, stars are much more complex than candles, but the principle is similar. Time leaves traces, and careful observers can learn to read those traces. Another factor that enters into the meaning of oldest is survival. Not every planet that forms will continue to exist for billions of years. Some may be destroyed in collisions, others may be stripped away by gravitational interactions with nearby stars. Some may spiral inward and fall into their host stars. The universe is a dynamic place, and stability over immense timescales is not guaranteed. So when we speak of the oldest planets, we're also talking about planets that have endured, worlds that formed long ago and managed to remain in orbit, undisturbed, for extraordinary lengths of time. That endurance itself is remarkable. Over billions of years, stars move through the galaxy. Stellar clusters disperse. Nearby supernovae may flood regions of space with radiation. Gravitational encounters can shift orbits or eject planets entirely. And yet, some planets continue circling their stars, quietly, steadily, year after year. There is something quietly reassuring about that image. The idea of a world continuing its orbit through ages beyond counting, unaffected by the passing of civilizations, the rise and fall of species, the changing shapes of continents. But there is another subtle point hidden in the question of age. Oldest compared to what? When astronomers say a planet is old, they often mean old compared to Earth. But Earth itself is already very ancient by human standards. A planet twice the age of Earth is not just old, it belongs to an entirely different era of cosmic history. To picture that, it helps to think about what the Milky Way was like when such a planet formed. Billions of years ago, the galaxy was a different place. The spiral arms were less defined. Many stars that exist today had not yet formed. The chemical composition of the galaxy was different as well. There were fewer heavy elements, because fewer generations of stars had lived and died to create them. That difference in chemistry turns out to be important. Rocky planets like Earth are made largely of elements heavier than hydrogen and helium, elements such as silicon, iron, oxygen, and magnesium. These elements were forged in the interiors of stars and scattered into space by supernova explosions. Early in the galaxy's history, those elements were less abundant. That means that forming rocky planets may have been more difficult in the earliest epochs. Gas giants, on the other hand, might have formed more easily, since hydrogen and helium were plentiful. So when astronomers search for the oldest planets, they are also studying the history of chemistry in the galaxy, tracing how the availability of planet-building materials changed over time. There is also a philosophical aspect to the idea of age in astronomy, one that emerges when we think about the difference between age and experience. A planet may be billions of years old, but what does that mean for the planet itself? Planets do not feel time the way living beings do. They do not remember. They do not anticipate. They simply exist, undergoing physical processes, cooling, shifting, eroding, orbiting. Time for a planet is not something noticed or measured. It is simply the background against which change occurs. And yet for us, contemplating such immense spans of time can be strangely calming. It places our own lives in a broader context. The worries of a single day, even a difficult one, seem smaller when set against the quiet persistence of worlds that have existed for billions of years. That perspective is one of the quiet gifts of astronomy. It does not solve our problems, but it reminds us of the vastness in which those problems reside. Returning to the scientific side of things, there is one more complication in defining the oldest planet. Detection methods have limits. We can only identify planets that are detectable with our current instruments. which means there may be older planets that remain undiscovered simply because they are too distant, too small, or orbit stars that are too faint to observe clearly. So when astronomers speak of the oldest known planet, they're careful with their wording. Known is an important word. It acknowledges that our knowledge is incomplete, that the universe is vast, and that many discoveries remain ahead. It is entirely possible that somewhere in the Milky Way there are planets older than any we have yet found, quietly orbiting ancient stars in remote regions of the galaxy, unnoticed for now. That thought carries a certain quiet wonder with it. The universe is not only vast in space but also in time, and our exploration of both is still in its early stages. Understanding age on a cosmic scale also requires us to think about how stars themselves age. Stars are not eternal. They are born, they evolve, and eventually they die. Some swell into red giants and shed their outer layers. Others explode as supernovae. Some leave behind white dwarfs, neutron stars, or black holes. A planet orbiting such a star may experience dramatic changes over time. Its climate may shift as the star brightens or dims. Its orbit may be altered by mass loss or gravitational interactions. In some cases, a planet may even survive the death of its star, continuing to orbit the remnant that remains. To understand how the oldest planets in the Milky Way came to exist, it helps to slow down and look carefully at how any planet forms at all. The process is not sudden, and it is not dramatic in the way explosions or collisions are. Planet formation is, above all, an exercise in patience. It unfolds gradually, quietly, over spans of time so long that even the lifetimes of stars feel brief by comparison. Everything begins in a cloud. Not a cloud like the ones drifting across the sky above us, but a vast cold cloud of gas and dust floating in interstellar space. These clouds, known as molecular clouds, can be dozens or even hundreds of light years across. They are mostly made of hydrogen, with smaller amounts of helium and traces of heavier elements, carbon, oxygen, silicon, iron, and many others, scattered within microscopic grains of dust. These clouds are not uniform. Some regions are denser than others, and occasionally something disturbs them. A nearby supernova might send a shockwave through the cloud. Two clouds might collide, or gravity might slowly begin to pull denser regions inward. Once gravity takes hold, the process becomes difficult to stop. A region of the cloud begins to collapse, slowly at first, then more quickly as the material gathers. As it collapses, it also begins to spin, because even a tiny initial rotation becomes amplified as the cloud shrinks, much like a figure skater pulling in their arms to spin faster. At the center of this spinning, collapsing cloud, matter gathers into a growing concentration that will eventually become a star. Around it, the remaining gas and dust flatten into a rotating disk, known as a protoplanetary disk. It is inside this disk that planets are born. At first, the disk is filled with tiny particles, grains of dust smaller than sand. They drift, collide, and sometimes stick together. At these scales, electrostatic forces can cause grains to cling, forming slightly larger clumps. Those clumps collide with others, and gradually, very gradually, they grow. This stage of planet formation is surprisingly delicate. Collisions must be gentle enough for particles to stick rather than shatter. Turbulence in the disk can either help or hinder the process. Gravity plays a role, but at small sizes, other forces matter as well. Over time, grains grow into pebbles. Pebbles gather into larger aggregates. Eventually, objects large enough for gravity to dominate begin to form. These are called planetesimals, and they may range from a few kilometers to hundreds of kilometers in size. Once planetesimals exist, the process accelerates. Gravity allows them to attract additional material more efficiently. Collisions between planetesimals can create larger bodies, sometimes merging, sometimes breaking apart, but gradually building upward in size. Given enough time, some of these bodies become protoplanets, worlds in the making. This stage can be chaotic. Protoplanets may collide in enormous impacts, reshaping entire worlds. Our own moon is thought to have formed when a Mars-sized body struck the young Earth, sending debris into orbit that eventually coalesced into the moon. But not all systems are as violent. Some planets may form in more orderly ways, accumulating material gradually over millions of years. The time required for this process varies, but in many cases planets can form within a few million to tens of millions of years after their star is born. That may sound long on human timescales, but astronomically speaking, it is relatively quick. The key ingredients in this process are gas, dust, and time. Dust provides the building material for rocky planets. Gas allows giant planets to form, especially if a solid core becomes massive enough to attract large envelopes of hydrogen and helium before the disk dissipates. Time allows collisions, accretion, and gravitational interactions to shape the system. And patience, if we may borrow a human word for a cosmic process, is essential. Nothing about planet formation is rushed. An interesting detail is that not every protoplanetary disk produces planets. Some disks dissipate before large bodies can form. Others may produce only small rocky worlds or only gas giants. Each system is shaped by its initial conditions, the mass of the disk, its temperature, its chemical composition, and the gravitational influences of nearby stars. This diversity is one reason why the exoplanets we have discovered are so varied. Some are hot Jupiters, gas giants, orbiting extremely close to their stars. Others are super-Earths, rocky planets larger than Earth but smaller than Neptune. Some orbit binary stars, moving through skies illuminated by two suns. Planet formation is not a single recipe. It is a family of processes, each unfolding in slightly different ways. When we consider the oldest planets, one factor becomes especially important: the composition of the disk. Early in the galaxy's history, heavy elements were less abundant. That means the dust available for building rocky planets was scarcer. In those early times, forming large rocky worlds may have been more difficult, though not impossible. Gas giants, which rely more on hydrogen and helium, might have been more common. This leads to an interesting implication. Some of the oldest planets in the Milky Way may not resemble Earth at all. They may be gas giants, or icy worlds, or planets orbiting stars very different from our Sun. Another aspect of planet formation is migration. Planets do not always remain where they form. Interactions with the disk can cause them to drift inward or outward. Gravitational encounters with other planets can also shift orbits dramatically. Some planets are even ejected from their systems entirely, becoming rogue planets drifting through interstellar space without a star. Over billions of years, planetary systems can change significantly. Orbits may become more stable or less so. Resonances can form, locking planets into regular patterns of motion. In some cases, late collisions can reshape worlds long after their initial formation. And yet, despite all this activity, many systems settle into long-term stability, with planets orbiting their stars in steady, predictable paths for billions of years. This stability is what allows very old planets to exist today. One of the most fascinating aspects of planet formation is that it is not a rare event. Observations of young stars show that protoplanetary disks are common. Many, perhaps most stars are likely to have planets. That realization has transformed our understanding of the galaxy. Planets are not unusual curiosities, they're a natural outcome of star formation, which means that from the earliest eras of the Milky Way, as soon as enough heavy elements were present, planets likely began to appear. Some of those early worlds may still be out there, orbiting ancient stars, silent witnesses to the long history of the galaxy. Another detail worth considering is how different environments influence planet formation. Stars often form in clusters, where many stars are born close together. In such environments, radiation from massive stars can strip away protoplanetary disks, potentially preventing planets from forming. Close stellar encounters can also disrupt disks or destabilize young planetary systems. On the other hand, quieter regions of space may allow disks to persist longer, giving planets more time to grow. The balance between these influences shapes the population of planets we observe today. When astronomers study very old stars, they often look at their chemical composition. Stars with very low metal content, meaning low abundances of elements heavier than helium, are typically very old. Finding planets around such stars suggests that planet formation was possible even when heavy elements were scarce. That realization has been one of the surprises of modern astronomy. Planets appear to be more resilient and adaptable than once thought. The universe found ways to build worlds even under conditions that seemed unfavourable. If we step back for a moment, there is something quietly reassuring in that idea. Given time, simple ingredients, and the steady pull of gravity, complexity can emerge. Dust can become stone. Stone can become worlds. And those worlds can endure for billions of years. If we want to understand why the very oldest planets in the Milky Way are so unusual, it helps to go back to a time before most planets could exist at all. Not just before Earth formed, and not even before our Sun existed, but back to the era when the galaxy itself was young, when the raw ingredients for building solid worlds were still in short supply. At first glance, that might sound surprising. The universe has always had stars, and wherever stars form, disks of gas and dust often appear around them. So it might seem natural to assume that planets have been forming steadily since the earliest times, but the earliest stars lived in a universe that was very different from the one we see today, and those differences mattered in ways that directly affected the chances of planet formation. To see why, it helps to think about what the universe was made of shortly after it began. In the aftermath of the Big Bang, the cosmos was remarkably simple in its chemical composition. Almost all of the matter consisted of hydrogen, with smaller amounts of helium and only tiny traces of lithium. That was essentially it. None of the heavier elements that make up rocks, metals and minerals existed yet. No carbon for organic molecules, no oxygen for water, no silicon for sand, no iron for planetary cores. Those elements had to be created later, inside stars. The first stars to form, sometimes called population 3 stars, were born from this simple mixture of hydrogen and helium. Without heavier elements to help cool the collapsing gas clouds, these early stars are thought to have been very massive, often tens or even hundreds of times the mass of the Sun. Massive stars burn their fuel quickly, shining intensely but living short lives, sometimes only a few million years before ending in powerful explosions known as supernovae. Those explosions were essential. Inside those stars, nuclear fusion created heavier elements, and when the stars died, those elements were scattered into space, mixing with the surrounding gas. Over time, this enriched material became part of new generations of stars. This gradual build-up of heavier elements is one of the most important long-term processes in the history of the galaxy. Astronomers often refer to elements heavier than helium as metals, even though many of them, like oxygen or carbon, would not be called metals in everyday language. The term is simply a convenient shorthand. Metallicity, the abundance of these heavier elements, plays a major role in planet formation. Dust grains, the tiny solid particles that serve as the seeds of planets, are made from these heavier elements. Without enough metals, there is very little solid material available to build rocky planets, or the cores of gas giants. So in the earliest eras of the Milky Way, where metallicity was low, planet formation was more difficult. Not necessarily impossible, but less efficient and less common. This is one reason why very old planets are rare. The conditions needed to build them did not exist in abundance until several generations of stars had already lived and died. There is also another factor to consider. The earlier stars formed in environments that were often more violent and crowded than many regions of the galaxy today. Star-forming regions were dense, and massive stars were more common. Massive stars produce intense radiation and powerful stellar winds, which can strip away the protoplanetary disks around nearby young stars. Without those disks, planets cannot form. Imagine trying to build a sandcastle while someone nearby is constantly blasting the sand away with a leaf blower. The raw material never has time to settle and accumulate. Over time, as the galaxy evolved, star-forming regions became somewhat calmer and the proportion of massive stars decreased. This allowed more protoplanetary disks to survive, long enough for planets to grow. So the earliest epochs of star formation were not particularly friendly to planet formation, especially for rocky planets like Earth. Still, the process of chemical enrichment continued. Each generation of stars contributed more heavy elements to the interstellar medium. Gradually, the galaxy became richer in the materials needed to build solid worlds. By the time stars like our Sun began to form, the galaxy had already gone through billions of years of this enrichment. That is one reason why our solar system contains a wide variety of elements, and why Earth has an iron core, silicate rocks, and abundant oxygen. But some stars formed earlier, in periods when metallicity was lower but not negligible. Around those stars, planets could form, though perhaps with different compositions and structures than the planets we're familiar with. Finding such ancient stars is one way astronomers search for very old planets. Many of the oldest stars in the Milky Way are found in globular clusters, which are dense spherical groups of stars orbiting the galaxy's centre. These clusters are among the oldest structures in the galaxy, with ages often exceeding 10 or 12 billion years. Globular clusters are fascinating places. A single cluster can contain hundreds of thousands of stars packed into a region only a few dozen light-years across. The night sky from a planet within such a cluster would look dramatically different from the sky we see on Earth. Instead of a few thousand visible stars, the sky could be filled with countless bright points of light, many far brighter than any star in our own night sky. But globular clusters also present challenges for planet formation and survival. Close stellar encounters are more common in such crowded environments. Gravitational interactions can disrupt planetary systems, altering orbits or even ejecting planets entirely. This makes the discovery of planets in globular clusters particularly intriguing, because it means that some planetary systems not only formed in these environments, but remained stable for billions of years despite the crowded conditions. Another clue about early planet formation comes from studying stars with very low metallicity that nevertheless host planets. These discoveries have shown that planets can form under conditions once thought unfavourable. The universe appears to be more flexible in its ability to build worlds than earlier models suggested. However, the types of planets that formed in those early times may have differed from the planets that formed later. Gas giants may have been more common than small rocky worlds, since the amount of solid material available to build large rocky planets was limited. This does not mean that rocky planets were absent, only that they may have been less frequent. There is also the question of time. Planet formation itself takes millions of years, and the earliest stars lived only a few million years before exploding. That means that some early planetary systems may have been disrupted before planets could fully form or stabilize. Later generations of stars with longer lifetimes and more stable environments provided better opportunities for planets to develop and persist. When astronomers study the oldest known planets, they often find that these worlds are associated with unusual types of stars or stellar remnants. Some orbit neutron stars or white dwarfs, objects that are the remnants of stars that have already completed their life cycles. This might seem strange at first. How could a planet survive the death of its star, especially when that death involves a supernova explosion? There are several possibilities. In some cases, planets may survive if they're far enough away from the star when it explodes. In other cases, planets may form after the explosion, from material that falls back into orbit around the remnant. These scenarios are complex and still being studied, but they show that planetary systems can be surprisingly resilient. Returning to the broader picture, the rarity of very old planets is not just a matter of detection. It reflects the history of the galaxy itself. Early conditions were less favourable for planet formation, and many early planetary systems may have been disrupted over time. So the ancient planets that do exist are survivors in more ways than one. They formed in an era when planet formation was more difficult, and they endured for billions of years in a dynamic and sometimes hazardous galactic environment. Thinking about that endurance can be quietly humbling. These worlds have been orbiting their stars for spans of time so long that entire generations of stars have formed and died in the same galaxy. The spiral arms of the Milky Way have shifted. The positions of stars relative to one another have changed, yet those planets continued their slow, steady orbits. Long before astronomers had the tools to discover planets around other stars, they were already studying the chemical makeup of stars themselves, carefully measuring the faint lines in starlight that reveal what elements are present. Those measurements led to an important realization that would later become central to the search for planets. Not all stars are made of exactly the same mixture of elements. Some contain higher proportions of heavier elements, while others are composed almost entirely of hydrogen and helium. That difference, subtle as it may sound, turns out to play a decisive role in whether planets can form at all. Astronomers use the term metallicity to describe this difference. In astronomy, metals include every element heavier than hydrogen and helium, so the word covers a wide range of substances, from carbon and oxygen to iron, silicon and nickel. These elements are not just minor details in the composition of a star, they are the essential building blocks of dust grains, rocks and ultimately planets themselves. If you picture the process of planet formation as a kind of construction project, metallicity determines how much building material is available. A star forming in a region rich in heavy elements is surrounded by a protoplanetary disk containing abundant dust, tiny solid particles that can stick together and grow. A star forming in a region with very low metallicity may still have a disk, but the amount of solid material within it is much smaller, which makes it more difficult for large solid bodies to form. This idea helps explain why planets were rarer in the early history of the Milky Way. The first generations of stars produced heavy elements through nuclear fusion and supernova explosions, but it took time for those elements to spread through the galaxy and become incorporated into new stars and their disks. Each generation of stars enriched the interstellar medium a little more, gradually increasing the metallicity of the galaxy as a whole. By the time our Sun formed, the galaxy had already undergone billions of years of chemical enrichment. The cloud of gas and dust that gave birth to the solar system contained enough heavy elements to form rocky planets, asteroids, and comets. Earth itself is made largely of these heavier elements, with iron in its core, silicon and oxygen in its crust, and a variety of other elements present in smaller amounts. If you travel back far enough in time, you find stars whose composition reflects a much earlier stage of galactic history. These stars contain only small fractions of heavy elements, sometimes less than 1% of the proportion found in the Sun. Finding planets around such stars is both challenging and fascinating, because it tells us that planet formation can occur even under conditions where building materials are scarce. To measure metallicity, astronomers analyze the light from stars using spectroscopy. When starlight is spread into a spectrum, dark lines appear at specific wavelengths where elements absorb light. Each element leaves a distinctive pattern of lines, allowing scientists to determine not only which elements are present, but also their relative abundances. This technique is precise enough to reveal subtle differences between stars. Some stars show strong lines from iron and other heavy elements, indicating high metallicity. Others show much weaker lines, suggesting that they formed earlier in the galaxy's history, before heavy elements became common. Over time, astronomers began to notice a pattern. Stars with higher metallicity were more likely to host giant planets, particularly gas giants similar to Jupiter. This correlation became clear in surveys of exoplanets. Stars rich in heavy elements seemed to be fertile ground for planet formation, while stars with very low metallicity hosted fewer detectable planets. One reason for this is related to the formation of gas giants. These planets are thought to form when a solid core built from heavy elements grows massive enough to attract a large envelope of gas from the surrounding disk. If there's not enough solid material to build that core quickly, the gas in the disk may dissipate before the planet can capture it, preventing the formation of a giant planet. Rocky planets also depend on metallicity, though perhaps in a slightly different way. Even small rocky worlds require sufficient dust to accumulate into planetesimals and protoplanets. When the supply of dust is limited, fewer such bodies may form, and those that do may remain small. Yet the universe often proves more flexible than our first models suggest. Observations have shown that planets can exist around stars with lower metallicity than once expected. Some of these planets may be smaller or less common, but they demonstrate that planet formation does not stop entirely in low metallicity environments. This finding is particularly important when searching for very old planets, because many ancient stars have low metallicity. If planet formation required high metallicity, the oldest stars would almost never host planets. But since planets have been found around some of these stars, we know that the process can operate under a wider range of conditions than previously thought. Another aspect of metallicity involves the types of elements present. Not all heavy elements contribute equally to planet formation. Elements like silicon, magnesium and iron are especially important for building rocky materials, while carbon and oxygen play major roles in forming molecules and ices. The exact balance of elements can influence the composition of planets, affecting everything from their density to their geology and atmosphere. For instance, a protoplanetary disk with a high carbon-to-oxygen ratio might produce planets with different mineralogy than those in a disk where oxygen dominates. Some scientists have even speculated about the possibility of carbon-rich planets, worlds where graphite or diamond might be more common than silicate rocks. While such planets remain hypothetical in many respects, the diversity of exoplanets discovered so far suggests that planetary composition can vary widely. Metallicity also affects the formation of smaller bodies like asteroids and comets. These objects are remnants of the planet formation process, preserving clues about the conditions in the early disk. In our own solar system, meteorites contain a record of the chemical environment that existed more than 4 billion years ago. Studying them has helped scientists understand how elements were distributed and how planetary building blocks formed. Looking outward to other star systems, astronomers must rely on indirect evidence, but the same principles apply. The chemical makeup of a star provides a window into the composition of the disk that surrounded it when its planets formed. When we think about the oldest planets in the Milky Way, metallicity becomes a kind of timeline. Stars with very low metallicity are often ancient, formed when the galaxy was still young. If such a star hosts a planet, that planet is likely to be extremely old as well. However, low metallicity does not always mean extreme age. Some regions of the galaxy have remained relatively metal poor even in later times, so astronomers must combine metallicity measurements with other data, such as stellar motion and position, to estimate ages more accurately. One of the most metal-poor environments where planets have been found is in globular clusters. These clusters contain stars that formed early in the galaxy's history, often with metallicities far below that of the Sun. Discovering planets in such clusters is difficult, partly because the stars are crowded together, making observations challenging, and partly because the low metallicity reduces the likelihood of planet formation. Nevertheless, at least one remarkable planetary system has been identified in such an environment, providing strong evidence that planets could form even when heavy elements were scarce. Thinking about metallicity also offers a broader perspective on the history of the galaxy. Every heavy element in your body, every atom of iron in your blood, every atom of calcium in your bones was created in stars that lived and died long before the Sun formed. The same is true for the materials that make up Earth and other planets. In a sense, planets are the descendants of stars assembled from the ashes of earlier generations. The metallicity of a star is a record of that ancestry, a measure of how many generations of stellar evolution contributed to the material from which it formed. Over billions of years, the Milky Way has become progressively richer in heavy elements. New stars forming today generally have higher metallicity than those that formed early in the galaxy's history. This gradual change has influenced the types of planetary systems that form, as well as the likelihood of forming complex rocky worlds. Returning to the question of the oldest planets, we can see why they are so rare. Not only did they have to form in environments where heavy elements were limited, but they also had to survive for billions of years in a galaxy that was still evolving. Some of these ancient planets may orbit stars that are themselves long-lived, small stars that burn their fuel slowly and remain stable for tens of billions of years. Others, as we will soon see, orbit stellar remnants, the remains of stars that have already passed through dramatic stages of evolution. The discovery of such planets has required careful observation, and sometimes a bit of good fortune, because the signals they produce are often faint and difficult to detect. Finding a planet around another star is already a delicate task, but identifying one that formed billions of years earlier than Earth adds another layer of difficulty. Age is not something we can measure directly for a planet the way we might date a rock on Earth. Astronomers must gather clues, often indirect ones, and piece them together carefully, much like investigators reconstructing a long-past event from faint traces that remain. To begin with, it helps to remember just how small and faint planets are compared to stars. A star shines by producing its own light through nuclear fusion. A planet, by contrast, usually reflects only a tiny fraction of the light it receives. Seen from many light years away, even a large planet is lost in the glare of its star, like a grain of dust floating near a powerful lamp. For this reason, most planets beyond our solar system are not seen directly. Instead, astronomers detect them by observing the effects they have on their surroundings, particularly on their host stars. These effects are subtle, but with precise instruments and patient observation, they can be measured. One of the earliest and most productive techniques is known as the radial velocity method. A planet does not simply orbit a star while the star remains motionless. Both bodies orbit their common centre of mass. Because the star is much more massive, its motion is small, but it is still there, a gentle wobble back and forth. As the star moves slightly toward us, and then away from us, the wavelength of its light shifts due to the Doppler effect. When the star moves toward us, its light is shifted slightly toward the blue end of the spectrum. When it moves away, the light shifts slightly toward red. By measuring these tiny shifts with extremely sensitive spectrographs, astronomers can detect the presence of a planet and estimate its mass and orbital period. This method has been used to discover many exoplanets, particularly large ones orbiting relatively close to their stars. It works best when the star is bright and stable, and when the planet's gravitational influence is strong enough to produce a measurable wobble. Another widely used technique is the transit method. If a planet's orbit happens to be aligned in such a way that it passes between its star and Earth, it will block a small fraction of the star's light for a short time. This produces a periodic dip in brightness that can be detected with sensitive photometers. The amount of dimming reveals the planet's size, while the timing of the transits reveals its orbital period. Space telescopes such as the Kepler mission and the Transiting Exoplanet Survey satellite have used this method to discover thousands of planets. However, detecting a planet is only the first step when searching for very old worlds. The next challenge is determining the age of the system. To estimate a planet's age, astronomers study its host star. Stars change over time in ways that can be modelled and measured. One important clue is the star's position on the Hertzsprung-Russell diagram, a chart that plots stars according to their luminosity and temperature. As stars age, they move through predictable stages of evolution, and by comparing observations with theoretical models, scientists can estimate how long a star has been shining. Chemical composition also provides clues. Stars with low metallicity often formed earlier in the galaxy's history, before heavy elements became abundant. Measuring the abundance of elements like iron relative to hydrogen gives astronomers a way to estimate when a star formed, though this method must be combined with others to improve accuracy. Stellar motion is another useful indicator. Very old stars often belong to populations that move differently from younger stars. Some travel in elongated orbits that take them far above and below the galactic plane, a sign that they formed in the early stages of the Milky Way's development. By measuring these motions, astronomers can identify stars that are likely to be ancient. Sometimes, astronomers also study star clusters, where all the stars formed at roughly the same time. Determining the age of the cluster gives a good estimate of the age of any planets found within it. Globular clusters in particular are valuable in this regard because many of them are more than 10 billion years old. Detecting planets in such clusters is challenging, partly because the stars are crowded together, making precise measurements difficult. But the reward is significant because any planet discovered there is almost certainly very old. There is also a more unusual method of planet detection that has proven especially important in the search for ancient worlds. This method involves pulsars, the rapidly rotating remnants of massive stars that ended their lives in supernova explosions. A pulsar emits beams of radio waves from its magnetic poles. As it rotates, these beams sweep across space like the beam of a lighthouse, producing extremely regular pulses of radio emission. Some pulsars are so precise that their pulses rival the accuracy of atomic clocks. If a planet orbits a pulsar, its gravitational influence can cause tiny variations in the timing of these pulses. By measuring these variations with extraordinary precision, astronomers can detect planets that might otherwise be impossible to find. The first confirmed exoplanets were discovered in this way, orbiting a pulsar known as PSRB 1257+12. These planets were unlike anything previously imagined, worlds orbiting the remnants of a dead star, a reminder that planetary systems can arise in unexpected places. Pulsar timing has also played a role in identifying some of the oldest known planets, because pulsars themselves can be very old, and because the environments in which they are found often include ancient stars, planets detected in these systems may have formed early in the history of the galaxy. Determining the age of such a system involves studying not only the pulsar, but also any companion stars and the surrounding stellar population. In some cases, astronomers can estimate the age of the entire system by analysing the properties of nearby stars or the cluster to which the system belongs. This process requires careful observation and often years of data collection. Tiny variations in timing, brightness, or spectral lines must be measured repeatedly to confirm the presence of a planet and to rule out other possible explanations. Another approach to finding very old planets involves gravitational microlensing. This technique relies on the bending of light by gravity, an effect predicted by general relativity. When a star passes in front of a more distant star, its gravity can act as a lens, magnifying the background star's light. If the foreground star has a planet, the planet's gravity can produce a brief additional brightening. Microlensing events are rare and unpredictable, but they can reveal planets at great distances, including planets orbiting very old stars in the galactic bulge. Because these events are brief and usually not repeatable, follow-up observations are challenging, but the method has expanded the range of planetary systems that astronomers can study. Each detection technique has its strengths and limitations. Radial velocity measurements are excellent for finding massive planets close to their stars. Transits are effective for determining sizes and atmospheric properties. Pulsar timing can detect extremely small planets, but applies only to a small number of systems. Microlensing can find distant planets, but provides limited information about their long-term behaviour. By combining these methods, astronomers have built a growing catalogue of exoplanets, including some that appear to be extremely old. Once a candidate ancient planet is identified, determining its age becomes a matter of combining evidence. The age of the host star, the chemical composition of the system, the motion of the star through the galaxy, and sometimes the age of a surrounding cluster all contribute to the final estimate. These estimates are not exact. There is always some uncertainty, sometimes hundreds of millions of years or more. But when the estimated age exceeds 10 or 12 billion years, the conclusion becomes clear. Such a planet must have formed early in the Milky Way's history. It is remarkable to think that light from such a system may have begun its journey toward Earth before our solar system even existed. By the time that light reaches our telescopes, it carries information about events that occurred in a distant and ancient past. Observing ancient planets also provides insights into the evolution of planetary systems over very long timescales. By comparing old systems with younger ones, astronomers can study how orbits change, how atmospheres evolve, and how stellar radiation affects planets over billions of years. In this way, the search for ancient worlds is not only about finding records of the past, it also helps us understand the future, including the long-term fate of our own solar system. As detection techniques continue to improve, new instruments promise to reveal even older and more distant planets. Next-generation telescopes, both on the ground and in space, will be able to measure starlight with greater precision and observe fainter objects than ever before. With those tools, astronomers hope to expand the inventory of ancient planets and refine our understanding of when and how the first worlds formed in the Milky Way. Far from our solar system, deep within a dense cluster of ancient stars, there exists a world that has quietly circled its host for longer than most of the Milky Way has been recognizable in its present form. This planet is known by the catalogue name PSRB 1620-26b, though it is often given a more memorable nickname, the Methuselah planet, a reference to the long-lived figure from ancient texts. The nickname is fitting because this world is believed to be roughly 12 to 13 billion years old, making it one of the oldest known planets ever discovered. Understanding how astronomers came to find such a planet and how they determined its age is a story that unfolds step by step, with each piece of evidence adding clarity to a picture that at first seemed almost unbelievable. The system in which this planet resides is located in a globular cluster called Messier 4, often abbreviated as M4. Globular clusters are among the oldest structures in the Milky Way. They formed early in the galaxy's history, and many of their stars are more than 12 billion years old. Messier 4 itself lies about 5,600 light-years from Earth in the direction of the constellation Scorpius, and it contains hundreds of thousands of stars packed into a region only a few dozen light-years across. That crowded environment makes globular clusters very different from the relatively quiet region of the galaxy where our Sun resides. Stars in such clusters pass closer to one another, and gravitational interactions are more common. For a long time, astronomers suspected that planetary systems might have difficulty surviving in these conditions. Close stellar encounters could disrupt orbits or eject planets entirely. So the discovery of a planet in such a cluster was surprising, and the particular nature of this system made it even more remarkable. At the centre of this discovery is not an ordinary star, but a pulsar, a type of neutron star formed when a massive star ends its life in a supernova explosion. A neutron star is incredibly dense. A teaspoon of its material would weigh billions of tons on Earth. Pulsars are neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, those beams sweep through space, producing pulses of radio waves that can be detected with radio telescopes. Some pulsars rotate with extraordinary precision, producing pulses so regular that they rival the accuracy of the best atomic clocks. This precision makes them extremely useful for detecting companions, because even tiny gravitational influences can alter the timing of the pulses. The pulsar in this system, PSRB 1620-26, rotates many times per second, and careful measurements of its pulses revealed something unusual. The timing variation suggested that the pulsar was not alone. It was part of a binary system, orbiting a white dwarf, the dense remnant of a star that has shed its outer layers after exhausting its nuclear fuel. That alone would not have been particularly surprising, because many pulsars are found in binary systems. But further analysis showed that the pulsar and white dwarf were themselves being influenced by a third object, something more distant, orbiting both of them. That third object turned out to be a planet. Detecting a planet in this way requires extraordinary precision. The gravitational pull of the planet slightly alters the motion of the pulsar and white dwarf, and those changes in turn affect the timing of the pulses detected on Earth. By carefully modelling these variations, astronomers were able to estimate the mass and orbit of the unseen companion. The planet is thought to be about 2 to 3 times the mass of Jupiter, making it a gas giant. It orbits the pulsar white dwarf pair at a distance roughly comparable to the distance between Uranus and the Sun, taking about a century to complete one orbit. What makes this planet especially remarkable is not just its unusual environment, but its age. Because the planet resides in Messier 4, and because the stars in that cluster formed more than 12 billion years ago, astronomers concluded that the planet must also be extremely old. Additional evidence from the properties of the white dwarf companion helped refine this estimate, suggesting that the system is indeed nearly as old as the cluster itself. This means that the planet formed when the universe was still very young, perhaps less than 1 billion years after the Milky Way began to take shape. At the time of this discovery, it challenged some assumptions about planet formation. Many astronomers had believed that planets, especially large ones, required relatively high metallicity to form efficiently, but the stars in Messier 4 have much lower metallicity than the Sun, indicating that planet formation was possible even when heavy elements were relatively scarce. That realization broadened our understanding of how early in cosmic history planets could appear. The history of this particular system is thought to be complex. The pulsar was once a massive star that exploded as a supernova, leaving behind a neutron star. The white dwarf companion was once a normal star that later evolved and shed its outer layers. The planet, meanwhile, must have formed before these dramatic events, or possibly during a later stage when material in the system reorganized. One scenario suggests that the planet originally formed around a normal star in the cluster. Later, through gravitational interactions common in such dense environments, that star may have exchanged partners with another system, eventually forming the unusual configuration we see today, with the planet orbiting a pulsar and white dwarf. Globular clusters are known for such interactions. Stars and their companions can exchange partners over time, reshaping systems in ways that would be rare in quieter regions of the galaxy. Despite this turbulent history, the planet survived. That alone is remarkable. Supernova explosions, stellar evolution, and gravitational encounters all have the potential to disrupt planetary orbits. Yet this world remains, continuing its slow orbit through an environment that has changed dramatically over billions of years. Imagining what conditions might be like on such a planet is an interesting exercise, though much remains uncertain. Being a gas giant, it would not have a solid surface like Earth. Its atmosphere would likely be composed primarily of hydrogen and helium, perhaps with traces of heavier elements. The radiation environment near a pulsar can be intense, though the planet's distance from the pulsar may reduce some of those effects. The sky from such a world, if one could somehow observe it, would be very different from the sky we see. Within the globular cluster, stars would be far more numerous and often brighter. True darkness might be rare, replaced by a constant glow of starlight from all directions. And above that crowded sky, the pulsar itself would be an extraordinary sight, though not in the way ordinary stars are. Pulsars are small, only about the size of a city, and they emit beams of radiation rather than steady visible light. The experience of observing such an object would be unlike anything familiar to us. But perhaps the most striking aspect of this planet is not what it looks like, but how long it has existed. 12 billion years is a span of time difficult to grasp. When this planet formed, the Milky Way was still assembling its structure. Many of the stars visible in our night sky today had not yet formed. The Sun itself would not appear for another 7 or 8 billion years. On Earth, the oldest rocks are about 4 billion years old, and the oldest known fossils date back more than 3 billion years. The Methuselah planet has existed for 3 times longer than life has existed on Earth. It has completed countless orbits around its hosts, each orbit taking roughly a century. That means it has circled its stars perhaps 100 million times since it formed. During that immense span of time, stars have been born and died, clusters have drifted, and the galaxy itself has continued its slow rotation. Yet the planet remains, a quiet participant in the long history of the cosmos. Discoveries like this one have changed the way astronomers think about planetary systems. They have shown that planets can form early, survive extreme events, and persist in environments far different from our own solar neighbourhood. They also remind us that the story of planet formation is more diverse than once imagined. Worlds can exist around pulsars, in globular clusters, and in systems shaped by gravitational encounters that rearrange their components over time. As more observations are made and more planets are discovered, astronomers continue to refine their understanding of how common such ancient worlds might be. The Methuselah planet may not be unique, though it remains one of the most striking examples known so far. Reflecting on such a world can be quietly calming in its own way. It is a reminder that the universe operates on timescales far beyond our daily experience, and that persistence, in the cosmic sense, is measured in billions of years rather than decades or centuries. In the broader picture, planets like PSRB 1620-26b serve as time capsules, preserving evidence of conditions that existed early in the history of the galaxy. By studying them, astronomers learn not only about the past, but also about the processes that continue to shape planetary systems today. And as we continue this journey, it becomes natural to ask what such an immense age really means in terms of planetary evolution. What happens to a world after billions upon billions of years? How do its atmosphere, its orbit, and its internal structure change over such long periods? Considering a world that formed billions of years before Earth requires a shift in perspective, because most of the ways we think about planets are shaped by the relatively short history of our own solar system. Earth, at about 4.5 billion years old, already feels ancient when measured against human history. Mountains have risen and worn away, oceans have opened and closed, entire branches of life have appeared, flourished, and vanished. Yet a planet like PSRB 1620-26b has existed for roughly 3 times longer than Earth has. That difference is so large that it changes the way we think about planetary lifetimes, stability, and the long-term evolution of worlds. One of the first things such an age tells us is that planetary systems can remain stable for extraordinarily long periods of time. It is easy to imagine that gravitational interactions, stellar evolution, or random disturbances might eventually disrupt orbits. But the existence of very old planets shows that stability can persist on timescales approaching the age of the galaxy itself. Orbits, once settled into a stable configuration, can continue with remarkable consistency, guided by gravity's steady influence. That stability is not absolute, of course. Over billions of years, many planetary systems do experience changes. Some planets migrate inward or outward. Others are ejected entirely after close encounters. But the fact that some systems remain intact for such immense spans suggests that long-term stability is not unusual, provided the initial conditions are favourable. Another lesson that emerges from studying ancient planets concerns the environments in which they formed. A planet more than 12 billion years old formed when the galaxy was still young, and when the abundance of heavy elements was lower than it is today. This confirms that planet formation did not require the relatively metal-rich conditions present in the solar neighbourhood when Earth formed. The threshold for planet formation appears to be lower than once believed, meaning that planets could begin appearing earlier in the history of the universe than earlier models predicted. This realization has broad implications. If planets could form early, then planetary systems may have been present throughout much of the galaxy's history, potentially providing environments where chemical processes, and perhaps even life, could arise far earlier than once assumed. Whether life actually developed in such environments is a separate question, one that remains open, but the presence of planets means that the physical settings existed. Age also influences the internal evolution of a planet. Over billions of years, a planet gradually cools as the heat left over from its formation escapes into space. Radioactive elements within the interior provide some additional heat, but their abundance decreases over time as they decay. This cooling can affect geological activity. On rocky planets, tectonic processes may slow or cease, volcanism may diminish. Magnetic fields, which depend on the motion of molten material in the interior, may weaken or disappear. For gas giants, the changes are somewhat different. These planets also cool and contract over time. When they are young, gas giants can be relatively warm and inflated. As they age, they radiate away internal heat and slowly shrink, becoming more compact. A gas giant that is more than 10 billion years old may look quite different from one that formed recently, even if their masses are similar. Atmospheres also evolve with time. High-energy radiation from the host star can gradually strip away lighter gases, particularly if the planet is close to the star. Chemical reactions driven by sunlight or other radiation can alter atmospheric composition. Over extremely long periods, these processes can transform a planet's appearance and climate. Another factor revealed by ancient planets is the durability of planetary material itself. Rocks, metals, and ices can persist for billions of years in the cold vacuum of space. On Earth, geological activity constantly reshapes the surface, recycling crust and erasing many of the oldest features. But on worlds without active tectonics, surfaces can preserve records of impacts and other events for immense spans of time. Our own moon provides an example on a smaller scale. Because it lacks atmosphere and active geology, its surface preserves craters that formed billions of years ago. A planet or moon that has remained geologically quiet for 10 or 12 billion years could retain a surface record stretching back almost to the beginning of the galaxy. Age also tells us something about the long-term evolution of stars and their influence on planets. Stars change as they age. Their brightness, temperature, and radiation output shift over time. A planet that has orbited its star for billions of years may have experienced very different conditions at different stages of the star's life. In the case of the Methuselah planet, the changes have been especially dramatic, because the star that once dominated the system has already completed its life cycle and become a white dwarf, while another star in the system collapsed into a neutron star. The planet has therefore survived not just gradual changes but extreme events, including a supernova explosion and the later evolution of a companion star. This resilience shows that planetary systems can endure events that might seem catastrophic. While some planets are certainly destroyed or ejected in such circumstances, others survive, continuing their orbits around stellar remnants. Looking at such a system also provides insight into the long-term dynamics of star clusters. Globular clusters like Messier 4 have existed for more than 10 billion years, orbiting the Milky Way's centre. Over that time, gravitational interactions between stars have altered orbits and reshaped systems. The survival of a planetary system in such an environment indicates that even in crowded and dynamic regions, stability is possible. Age also brings perspective on the scale of cosmic history. When a planet is 12 or 13 billion years old, it formed when the universe itself was only about 1 billion years old. That was a time when galaxies were still assembling, when the first large structures were taking shape, and when the chemical enrichment of the cosmos was still in its early stages. Imagining that era can be challenging. The night sky, if one could have observed it from such a planet, would have been different. The Milky Way would have had a different structure, and many of the stars we see today would not yet have existed. The cosmic environment itself was changing. with star formation rates higher than they are now. Another important point is that the existence of very old planets places constraints on theories of galaxy evolution. Models of how quickly heavy elements accumulated, how stars formed, and how planetary systems developed must all be consistent with the presence of planets at such early times. Observations of ancient planets therefore serve as tests of these models, helping astronomers refine their understanding of the galaxy's history. There is also a broader implication concerning the longevity of planetary systems in general. Our own solar system is about 4.6 billion years old and is expected to remain relatively stable for several billion more, though conditions on Earth will change as the sun gradually brightens. The existence of planets that have already endured for 12 billion years suggests that planetary systems can persist for much longer than the current age of our own. That realization can change the way we think about the future. The sun will eventually evolve into a red giant and shed its outer layers, transforming the inner solar system. But some outer planets may survive, orbiting the remnant white dwarf that will remain. In that sense, systems like the one containing the Methuselah planet may offer a glimpse of what distant futures can look like. Another aspect of age that often goes unnoticed is the accumulation of impacts. Over billions of years, planets and moons are struck by asteroids and comets countless times. In the early solar system, impacts were far more frequent than they are today. An ancient planet may have experienced an even longer history of collisions, gradually shaping its surface and perhaps its internal structure. In gas giants, impacts may not leave permanent scars in the same way, but they still contribute to the mixing and evolution of the atmosphere. Over billions of years, even rare events can accumulate into significant changes. Thinking about such immense spans of time can be strangely calming. It places human history in a wider context, reminding us that the universe moves at its own pace, unhurried and steady. The slow processes that shape planets and stars operate over timescales far beyond our daily concerns. Yet these ancient worlds are not merely distant curiosities. They are part of the same galaxy we inhabit, orbiting the same central mass, sharing the same cosmic neighbourhood, even if separated by vast distances. As astronomers continue to search for and study very old planets, they are learning not only about the past, but also about the diversity of planetary systems and the many paths their evolution can take. Each discovery adds another piece to the story of how worlds form, change, and endure. And when we consider planets that have existed for billions of years longer than Earth, it naturally leads to another question. What kinds of environments do these ancient worlds inhabit? What is it like to orbit within the dense ancient stellar populations where many of them are found? Picture a night sky where darkness never fully settles in. Instead of a few thousand stars scattered across the heavens, the sky glows with countless points of light, some so bright that they cast faint shadows. Constellations, as we know them, would be impossible to trace because there would be far too many stars crowded together in every direction. This is the kind of environment that exists inside a globular cluster, one of the oldest and most densely populated stellar neighbourhoods in the Milky Way. Globular clusters are remarkable structures. Each one is a nearly spherical collection of stars bound together by gravity, often containing hundreds of thousands of stars packed into a region only a few dozen light-years across. To put that in perspective, the nearest star to our Sun, Proxima Centauri, lies more than 4 light-years away. In many parts of a globular cluster, the average distance between stars can be a fraction of that, sometimes less than 1/10 of a light-year. That closeness changes everything about the environment in which planets exist. In our solar neighbourhood, the Sun and its planets travel through space in relative isolation. Nearby stars are distant enough that their gravitational influence on the solar system is extremely weak. Over billions of years, passing stars can slightly perturb the outermost regions, particularly the distant cloud of icy bodies far beyond Neptune, but the inner planets remain largely undisturbed. Inside a globular cluster, however, stars pass much closer to one another. Over millions and billions of years, these close encounters can alter planetary orbits, or even remove planets from their systems entirely. A planet drifting too far from its star might be captured by another star or ejected into interstellar space. For a long time, astronomers believed that such environments would be too unstable for planetary systems to survive. The reasoning seemed straightforward. If stars are constantly passing nearby, their gravitational pull would disrupt the delicate architecture of planetary orbits. Over enough time, most systems would be dismantled. Yet the discovery of planets in globular clusters has shown that survival is possible, even in these crowded conditions. Stability does not require perfect isolation. It requires only that close encounters remain infrequent enough, or distant enough, that the gravitational tugs do not accumulate into catastrophic changes. In fact, many stars in globular clusters reside in regions where the density is lower than in the crowded core, and in those outer regions, planetary systems may remain relatively undisturbed for long periods. Even in denser regions, the timescale between close encounters can still be millions of years, long enough for planets to continue their orbits largely unchanged. Another striking difference between globular clusters and the region around the Sun is the age of the stars. Most stars in a globular cluster formed at roughly the same time, more than 10 billion years ago. They are ancient by stellar standards, and many of the more massive stars have already evolved into white dwarfs, neutron stars, or black holes. This means that a planetary system in such a cluster is not only living in a crowded environment, but also in one that has been evolving for an immense span of time. Stars have changed, died, and sometimes exchanged companions through gravitational interactions. The cluster itself has orbited the galaxy's centre many times, gradually losing stars at its edges as tidal forces pull them away. Despite all this activity, the cluster remains bound together, a long-lived community of stars moving through the galaxy as a unit. The brightness of the night sky in such a place would be one of its most noticeable features. On Earth, the Milky Way appears as a faint band of light, visible only under dark skies. Inside a globular cluster, the combined light of nearby stars could produce a constant twilight, depending on the planet's location. Some stars might appear larger and brighter than any star in our sky, simply because they would be so much closer. The presence of many nearby stars also raises interesting questions about temperature and radiation. While the combined light of distant stars would not significantly heat a planet, occasional nearby stars passing at relatively close distances could influence the radiation environment over long time scales. A passing star might brighten the sky for thousands of years before gradually drifting away again. Such encounters would unfold slowly, far too slowly to notice within a single lifetime, but over millions of years they could alter the background brightness of the sky in subtle ways. Another aspect of globular clusters that distinguishes them from younger regions of the galaxy is their chemical composition. As discussed earlier, these clusters formed when heavy elements were less abundant. Their stars tend to have lower metallicity, which affects the kinds of planets that can form. Rocky planets may be less common, and gas giants may dominate among the planets that do exist. Even so, the presence of planets like Pulsar b 1620-26b demonstrates that planet formation was not prevented entirely by low metallicity. The universe found ways to build worlds even with limited resources. Life in such a cluster, if it existed, would experience a sky and a sense of time very different from ours. Day and night would still depend on the rotation of the planet and the presence of a nearby star, but the broader environment would be far less empty. The idea of deep, starless darkness might be unfamiliar. It is interesting to consider how such a sky might affect the development of astronomy for any observers living there. On Earth, the relative sparseness of the night sky makes patterns and constellations easy to recognize. In a globular cluster, the sheer number of stars might make it difficult to distinguish individual constellations, though bright nearby stars could dominate the view in certain directions. Distances between stars would also be easier to appreciate. Some stars would visibly shift position over the course of centuries as they move through the cluster, a motion too small to notice in a human lifetime on Earth, but potentially detectable in a denser stellar environment. From a scientific perspective, globular clusters provide valuable laboratories for studying stellar evolution and dynamics. Because the stars formed at roughly the same time, differences between them are largely due to their initial masses rather than age. This allows astronomers to test models of stellar evolution by comparing stars at different stages of their life cycles within the same cluster. For planets, the long lifetimes of these clusters offer an opportunity to study what happens to planetary systems over extremely long periods. The existence of planets in such environments suggests that planetary systems can endure not only the slow changes of stellar evolution, but also the gravitational interactions that occur in crowded stellar populations. Another intriguing possibility is the existence of rogue planets within globular clusters. Close encounters between stars can strip planets from their systems, leaving them to wander through the cluster independently. These free-floating planets would not orbit any star, though they would still be bound to the cluster as a whole, drifting through the gravitational field of the surrounding stars. Such worlds would be cold and dark, illuminated only by distant starlight. If they retained thick atmospheres or internal heat, they might still possess subsurface oceans or other interesting environments, though studying such planets directly would be extremely challenging. The long-term evolution of globular clusters also affects their planetary systems. Over billions of years, clusters gradually lose stars as gravitational interactions and tidal forces from the Milky Way pull stars away. This slow process, known as evaporation in a dynamical sense, changes the density and structure of the cluster. As the cluster evolves, the likelihood of close stellar encounters may decrease in some regions, potentially making planetary systems more stable in later epochs than in the early history of the cluster. Thinking about the immense age of these clusters also brings perspective to the idea of continuity in the universe. While individual stars live and die, and while planetary systems may form and change, the cluster itself can persist for billions of years, maintaining its identity even as its components evolve. A planet within such a cluster could experience a history stretching back to the early epochs of the Milky Way, witnessing changes in the cluster's structure and in the stars around it, though of course not in any conscious sense. Its orbit would continue, steady and predictable, while the surrounding stellar population slowly shifted. One of the most fascinating aspects of these environments is how different they are from our own, yet how they are governed by the same physical laws. Gravity, radiation, and orbital mechanics operate in exactly the same way, whether in the quiet outskirts of a spiral arm or in the crowded heart of a globular cluster. The differences arise from initial conditions, density, and time. The discovery of planets in globular clusters has also encouraged astronomers to continue searching for more such worlds. Each new detection helps refine our understanding of how common planets are in these ancient environments, and how planetary systems respond to long-term gravitational interactions. As telescopes become more sensitive and data analysis techniques improve, it is likely that additional planets will be found in clusters, perhaps including smaller rocky worlds that are more difficult to detect with current methods. Considering the vast timescales involved, it is possible that some of these planets have existed for nearly the entire history of the Milky Way. They formed when the galaxy was young and have persisted through billions of years of gradual change. Reflecting on such places can be quietly grounding. It reminds us that our solar system is just one example among many, and that the universe contains environments far different from anything we experience here. Time leaves marks on everything, but the way those marks appear on a planet depends very much on the kind of planet it is, the star it orbits, and the environment it inhabits. When we think about worlds that have existed for 10 or 12 billion years, we are imagining objects that have had far longer than Earth to cool, to settle, and to evolve under the steady influence of gravity and radiation. The changes are not dramatic in the way a volcanic eruption or an impact might be. Instead, they are gradual, unfolding over spans of time so long that no single event stands out. The overall effect, however, can be profound. One of the first changes that affects any planet over immense timescales is internal cooling. When planets form, they begin hot. Energy from impacts, compression, and radioactive decay keeps their interiors warm, sometimes molten. Over time, that heat slowly escapes into space. On rocky planets, this cooling affects geological activity. Early in a planet's history, volcanoes may be frequent. Tectonic plates may move vigorously, and the surface may be reshaped repeatedly. As billions of years pass, these processes often slow down. The crust thickens, volcanic activity diminishes, and tectonic motion may eventually cease altogether. Mars provides an example on a smaller scale. It was once more geologically active than it is today, with volcanoes, flowing water, and perhaps a thicker atmosphere. Over time, as the planet cooled and its interior became less dynamic, much of that activity faded. Now Mars is comparatively quiet, its surface preserving ancient features that formed billions of years ago. An even older rocky planet might be quieter still. Its surface could be heavily cratered, marked by impacts accumulated over vast spans of time. Without tectonics or erosion to erase those scars, they would remain, a record of the planet's long exposure to space. Mountains might have worn down, slopes softened by slow processes of temperature change and micrometeorite impacts. The landscape, if there were one, might look subdued, shaped by age rather than activity. Atmospheres also change over time. A young planet may have a thick atmosphere rich in gases released from volcanic eruptions. Over billions of years, lighter gases can escape into space, especially if the planet has low gravity or lacks a strong magnetic field. Radiation from the host star can break apart molecules, gradually altering the composition of the atmosphere. In some cases, the atmosphere may thin dramatically, leaving a world exposed to the vacuum. Venus and Mars illustrate different paths of atmospheric evolution within our own solar system. Venus retains a thick atmosphere, though its composition and temperature have changed dramatically. Mars, by contrast, lost much of its atmosphere over time, leaving behind a thin envelope of gas. An ancient planet could follow either path, depending on its mass, magnetic field, and proximity to its star. Gas giants experience their own long-term changes. These planets begin relatively warm, still radiating heat left over from their formation. Over billions of years, they cool and contract slightly. Their cloud patterns and atmospheric dynamics may shift as internal heat decreases. The colours and structure of their atmospheres could change gradually, influenced by chemistry and radiation. Jupiter, for example, still radiates more heat than it receives from the Sun, but that internal heat will diminish over time. A gas giant that is billions of years older than Jupiter would likely be cooler and somewhat less luminous in the infrared, though still massive and stable. The stars these planets orbit also evolve, and that evolution influences planetary appearance. A star brightens gradually during much of its lifetime. Our Sun, for instance, is about 30% brighter now than when Earth formed. That increase has significant consequences for planetary climates. Oceans can evaporate, ice caps can melt, and atmospheric chemistry can change. On very long timescales, stars may undergo more dramatic transformations. A Sun-like star eventually expands into a red giant, engulfing or scorching nearby planets and altering the orbits of more distant ones. Some planets may be destroyed, while others survive in modified orbits around the stellar remnant. In systems like the one containing the Methuselah planet, the changes have been especially extreme. The original massive star exploded as a supernova, leaving behind a neutron star. another star in the system evolved into a white dwarf. The planet now orbits these remnants, receiving very different radiation than it would have during the early stages of the system's history. If one could somehow observe such a planet over billions of years, the changes in its sky would be among the most noticeable features. Stars would shift position gradually as the cluster moved and evolved. Some nearby stars would brighten and fade as they aged, while others would end their lives and disappear entirely, leaving behind faint remnants. Another effect of age is the accumulation of impacts. Asteroids and comets continue to collide with planets over billions of years, though the frequency of large impacts usually decreases after the early stages of planetary system formation. On an ancient world, the surface might preserve a record of these impacts stretching back almost to the beginning of the system. Craters of many different ages would overlap, forming a complex pattern that tells a long story of collisions. For icy worlds, slow processes such as sublimation and redeposition of ice could reshape the surface over time. Temperature variations, radiation, and micrometeorite impacts gradually alter the texture and composition of the surface layers. Some icy moons in our solar system already show signs of these processes, and over much longer periods the cumulative effect could be significant. Magnetic fields are another feature that may change with age. A magnetic field is generated by the motion of electrically conducting fluid in a planet's interior. As the interior cools and solidifies, that motion may slow or cease, weakening the magnetic field. Without a magnetic field, a planet's atmosphere is more vulnerable to being stripped away by stellar winds and radiation. Earth's magnetic field has persisted for billions of years, but it will not last forever. On a planet older than Earth, the field might already have weakened or disappeared, with consequences for the atmosphere and surface conditions. Even the colour of a planet might change over long timescales. Chemical reactions driven by sunlight or radiation can alter surface minerals, darkening or reddening them. On airless bodies, exposure to cosmic rays and micrometeorite impacts gradually modifies the surface, a process known as space weathering. The result is a surface that becomes darker and more uniform over time. Considering all these processes together, the oldest planets may not appear dramatically different at a glance, but they would carry subtle signs of age in their temperature, geology, atmosphere, and orbital environment. They would be quieter worlds in many respects, shaped more by slow change than by rapid transformation. There is also an emotional aspect to imagining such ancient worlds, though it arises from our own perspective rather than anything intrinsic to the planets themselves. Thinking about a planet that has existed for 12 billion years can create a sense of continuity, a reminder that the universe has been evolving long before our species appeared and will continue long after. At the same time, these worlds are not static relics. They remain part of an active galaxy, orbiting stars, interacting gravitationally with their surroundings and responding to changes in their environment. Age does not mean stillness. It means long participation in the ongoing processes of the cosmos. Another interesting point is that the oldest planets might not always be easy to recognize as such. Without precise measurements of their host stars and environments, a very old planet might appear similar to a younger one of the same mass and composition. Age often reveals itself indirectly, through the characteristics of the star, the chemical composition of the system, and the broader galactic context. As astronomers continue to refine their techniques, they are learning to read these clues more effectively, identifying planets that formed in the early history of the Milky Way, and studying how they have evolved over immense spans of time. Reflecting on the appearance of these ancient worlds naturally leads to another question. If planets can endure for billions of years, could some of them remain habitable for equally long periods? What conditions would be required for a planet to sustain an environment suitable for life over such immense timescales? Habitability is often discussed in connection with planets that resemble Earth, but when we begin thinking about worlds that are billions of years older than our own, the question becomes more complicated and in some ways more interesting. Age alone does not determine whether a planet can support life. What matters more are temperature, the presence of liquid water or other solvents, atmospheric stability, and a source of energy. A planet can be very old and still meet some of these conditions, or it can be relatively young and completely inhospitable. So the real question is not simply whether ancient planets exist, but whether any of them could remain stable and life-friendly over immense stretches of time. To begin answering that, it helps to consider what makes Earth habitable in the first place. Our planet lies at a distance from the Sun where temperatures allow liquid water to exist on the surface. It has an atmosphere thick enough to retain heat, but not so thick that it traps too much. It has a magnetic field that shields the surface from much of the solar wind, and it has active geology that recycles carbon and other elements through processes like plate tectonics and volcanism. All of these factors contribute to maintaining conditions suitable for life over billions of years. However, none of these conditions are guaranteed to last forever. The Sun is gradually becoming brighter, and in about 1 billion years Earth's oceans may begin to evaporate, making the surface far less hospitable. This means that even a planet that starts out habitable may lose that status long before it reaches an age of 10 or 12 billion years. That observation suggests that long-term habitability requires a delicate balance between planetary and stellar evolution. A small, stable star that changes very slowly offers the best chance for a planet to remain habitable over extremely long timescales. Red dwarf stars, for example, burn their fuel so slowly that they can shine for tens or even hundreds of billions of years. A planet orbiting such a star could, in principle, remain in the habitable zone for a very long time, provided other conditions are favourable. Ancient planets found in globular clusters or other old stellar populations often orbit stars that are smaller and longer lived than the Sun. That alone increases the possibility that habitable conditions could persist for extended periods. But there are also challenges. One of the main difficulties for habitability in ancient systems is the low metallicity of the stars and the disks from which their planets formed. Lower metallicity means fewer heavy elements available to build rocky planets with thick crusts, large iron cores, and potentially strong magnetic fields. Such planets may exist, but they might be smaller or less geologically active than Earth, which could affect their ability to maintain stable climates. Atmospheric retention is another concern. Over billions of years, a planet can lose much of its atmosphere through processes such as thermal escape, sputtering by stellar winds, and chemical reactions driven by radiation. A strong magnetic field helps protect an atmosphere, but as mentioned earlier, magnetic fields may weaken as a planet's interior cools. An ancient planet might therefore have lost much of its atmosphere long ago, leaving it cold and dry. Yet not all forms of habitability require Earth-like surface conditions. Beneath the icy shells of moons such as Europa and Enceladus in our own solar system, there are likely subsurface oceans kept warm by tidal heating. These environments are shielded from radiation and may remain stable for billions of years. A similar situation could exist on ancient planets or moons in other systems, where internal heat or tidal forces maintain liquid water below the surface even after the surface has frozen. In such environments, life, if it arose, might persist far longer than it could on the surface of a planet exposed to changing stellar radiation. The absence of sunlight would limit photosynthesis, but other forms of metabolism, based on chemical energy, could be possible, as they are around hydrothermal vents on Earth's ocean floor. Another factor to consider is the stability of orbits. A planet's climate depends strongly on the regularity of its orbit. Large changes in orbital distance or tilt can produce extreme climate shifts that challenge the survival of life. Ancient planetary systems that have remained dynamically stable for billions of years may offer relatively steady conditions, at least in this respect. Radiation environments also matter. In globular clusters, stars are closer together, and nearby supernovae may have been more common in the past. Intense bursts of radiation could sterilize planetary surfaces or strip away atmospheres. However, these events are relatively rare on timescales of billions of years, and planets located in quieter regions of a cluster might avoid the worst effects. Interestingly, the very age of some systems could work in favour of habitability in certain respects. The most massive and short-lived stars, which produce the most energetic radiation and supernova, have long since disappeared from old clusters. What remain are smaller, longer-lived stars that evolve more slowly and produce less intense radiation. In that sense, an ancient cluster may be calmer now than it was in its youth. Another aspect of habitability that becomes important over immense timescales is biological evolution. On Earth, life appeared relatively quickly after conditions became suitable, but complex life took billions of years to develop. A planet that has remained habitable for 10 billion years would have had far more time for evolution to proceed, assuming life arose there in the first place. Of course, this is speculative, because we do not yet know how often life arises even under favourable conditions, but the possibility is intriguing. Ancient planets, if habitable, could host ecosystems far older and potentially more complex than anything on Earth, simply because they have had more time. There is also the question of energy sources. Even if a planet loses its atmosphere or surface water, life might persist underground using geothermal energy. On Earth, microbes have been found kilometres below the surface, living in conditions once thought too extreme to support life. These environments are stable over long periods, shielded from surface changes and external radiation. An ancient planet with a warm interior could, in principle, support similar forms of life for billions of years, even if its surface appears barren. Tidal heating provides another potential energy source. In systems where a planet or moon experiences strong gravitational interactions with nearby bodies, tidal forces can generate heat within the interior. This process can keep subsurface oceans liquid and drive geological activity long after the planet would otherwise have cooled. In the case of planets orbiting stellar remnants such as white dwarfs, habitability presents additional challenges. The earlier stages of stellar evolution may have stripped away atmospheres or subjected planets to intense radiation. However, some studies suggest that habitable conditions could arise again around white dwarfs if planets migrate into the habitable zone after the star is stabilized. These scenarios remain theoretical, but they show that habitability is not limited to a single type of environment. Looking beyond individual planets, the broader environment of an ancient stellar population also influences habitability. In a globular cluster, the proximity of other stars means that gravitational interactions could perturb comet clouds or asteroid belts, increasing the likelihood of impacts. While occasional impacts are not necessarily catastrophic for life, frequent large impacts could pose challenges for long-term stability. Still, the survival of planets in such environments for billions of years suggests that catastrophic disruptions are not inevitable. Many systems may experience long periods of relative calm. Thinking about habitability over immense timescales also highlights how temporary even favourable conditions can be. Earth has been habitable for billions of years, but it will not remain so indefinitely. Climate, stellar evolution, and geological processes all change with time. A planet's habitability is a phase, not a permanent state. Ancient planets remind us that these phases can last longer than we might expect, but they also emphasize that change is inevitable. The search for habitable worlds often focuses on planets similar to Earth, orbiting sun-like stars. But the study of ancient planets encourages a broader view. Habitability may arise in many different forms, some of which we have not yet imagined. As telescopes become more powerful and detection methods improve, astronomers may one day be able to study the atmospheres of very old planets directly, looking for chemical signatures that could indicate biological activity. Such discoveries would transform our understanding of life in the universe. For now, the question of whether ancient planets can remain habitable remains open, but the evidence suggests that at least some of them could, under the right conditions, maintain environments where life might persist for extraordinary lengths of time. If you could move backward through the history of the Milky Way, not in a sudden jump but gradually, watching the galaxy change as millions of years passed like slow-moving clouds, the scene would become noticeably different long before you reached the time when the oldest known planets were forming. The familiar spiral arms would still exist, but their shapes would be less settled, their structure more uneven. Some of the stars that light our night sky today would not yet have formed, and others would be in very different stages of their lives. To understand what the galaxy looked like in those distant epochs, it helps to remember that galaxies are not static objects. They evolve. Stars are born, live out their lives, and die, returning material to space. Gas clouds drift, collide, and collapse. Star clusters form and gradually disperse. Over billions of years, these processes reshape the galaxy in ways that are subtle from one moment to the next, but dramatic over immense spans of time. More than 12 billion years ago, the Milky Way was still relatively young. The universe itself was only a few billion years old. The galaxy had already begun forming stars, but its chemical composition was different from what we see today. Heavy elements were less abundant because fewer generations of stars had lived and died to produce them. Hydrogen and helium dominated, and the clouds from which new stars formed contained only modest amounts of the heavier materials needed to build rocky planets. Star formation, however, was often more active than it is now. In the early universe, galaxies contained more cold gas, the raw fuel for making stars. Regions of the Milky Way were filled with vast molecular clouds where new stars ignited in clusters, sometimes in great numbers. The night sky in those eras, if one could have observed it from a suitable vantage point, might have appeared richer in bright, massive stars, many of which burned intensely but briefly. These massive stars played an important role in shaping the early galaxy. Their radiation and stellar winds stirred the surrounding gas, and when they exploded as supernovae, they enriched the interstellar medium with heavier elements. Each explosion was both an ending and a beginning, scattering the materials that would eventually become parts of future stars, planets, and perhaps even living organisms. Globular clusters, like the one that hosts the Methuselah planet, were already ancient even then. Many of them formed very early in the galaxy's history, possibly during the period when the Milky Way itself was assembling from smaller proto-galactic fragments. These clusters orbited the young galaxy much as they do today, though their orbits and internal structures have evolved over time. Inside such a cluster, the view of the galaxy would have been different from what we see from Earth. The dense concentration of nearby stars would dominate the sky, and the broader structure of the Milky Way might appear as a faint, diffuse glow beyond the crowded foreground. The cluster itself would feel like a self-contained stellar city, with countless suns shining in every direction. Beyond the clusters, the galactic disk was still taking shape. Spiral arms are not permanent, rigid structures. They are patterns created by density waves moving through the disk, compressing gas and triggering star formation. Over billions of years, these patterns shift and evolve. The spiral arms we see today are not exactly the same as those that existed billions of years ago. The central bulge of the galaxy, a dense region of older stars surrounding the supermassive black hole at the Milky Way's core, was already in place, though its structure has likely changed as stars moved and interactions redistributed matter. The black hole itself, now known as Sagittarius A star, had probably already grown to a significant fraction of its current mass, though it may have been more active in the past, occasionally drawing in gas and emitting bursts of radiation. One of the most noticeable differences in the early Milky Way would have been the abundance of gas. Over time, star formation gradually consumes gas, converting it into stars and planets. While gas continues to flow into the galaxy from intergalactic space, the overall supply decreases slowly as the galaxy ages. Billions of years ago, there was simply more raw material available, and star-forming regions may have been more common. This increased activity also meant that the galaxy was a somewhat more energetic place. Supernova explosions occurred more frequently, and radiation from massive stars was more intense in certain regions. For planetary systems forming in these environments, conditions could be challenging. Protoplanetary disks might be exposed to strong ultraviolet radiation, and nearby explosions could disturb or even strip away material. Yet even in such conditions, some planetary systems managed to form and endure. The Methuselah planet is one example, a survivor from an era when the galaxy was still in the process of building up the heavy elements that make planets possible. Another difference between the Milky Way long ago and the galaxy we know today lies in the distribution of stars. Over billions of years, stars move through the galaxy, their orbits shaped by gravitational interactions and the overall mass distribution of the galactic disk and halo. A star that is now near the Sun may have formed in a very different region and migrated over time. This process of radial migration means that the present arrangement of stars does not perfectly reflect where they were born. The galaxy is a dynamic system, with stars slowly shifting positions over immense spans of time. Ancient planets, therefore, may have travelled through different regions of the galaxy during their lifetimes, experiencing varying environments as they moved. The halo of the Milky Way, a vast spherical region surrounding the disk, contains many of the oldest stars and globular clusters. In the early epochs, this halo may have been more active, containing remnants of smaller galaxies that merged with the growing Milky Way. Evidence of these mergers can still be seen today in streams of stars moving together through the halo, the remains of dwarf galaxies torn apart by tidal forces. Such mergers were more common in the past, and they contributed to the growth of the galaxy. When smaller galaxies merged with the Milky Way, they brought their own stars, gas, and possibly planetary systems. Some of the oldest planets we might one day discover could have formed not in the Milky Way itself, but in smaller galaxies that were later absorbed. Thinking about this can broaden the sense of history even further. A planet orbiting quietly today might have originated in a completely different galactic environment billions of years ago, long before becoming part of the Milky Way. The overall brightness of the galaxy may also have been different in those distant times. With more active star formation and more massive stars, certain regions could have been brighter and more energetic. Over time, as star formation rates declined and massive stars became less common, the galaxy settled into a somewhat calmer state. Another aspect to consider is the cosmic background radiation, the faint afterglow of the Big Bang. Billions of years ago, this radiation was slightly warmer and more intense than it is today, though still far colder than any environment suitable for life. Its influence on planetary conditions would have been minimal, but its presence serves as a reminder that the universe itself was younger and denser. For any observers who might have existed on a very ancient planet, the night sky would have looked subtly different in other ways as well. Some nearby galaxies would have appeared slightly closer, because the universe has been expanding over time, increasing the distances between galaxies. The Andromeda Galaxy, for example, is gradually approaching the Milky Way now, but billions of years ago it would have been farther away and perhaps less prominent in the sky. The large-scale structure of the universe changes slowly, but given enough time, those changes become noticeable. Ancient planets have existed long enough to witness, in a purely physical sense, the gradual shifting of galaxies across cosmic distances. Returning to the Milky Way itself, one of the most important differences in the early galaxy was the lower abundance of elements like iron, silicon, and oxygen. This meant that rocky planets were likely less common, and those that did form may have been smaller or compositionally different from Earth. Gas giants, which rely more on hydrogen and helium, may have been relatively more frequent among the earliest planetary systems. Over time, as successive generations of stars enriched the interstellar medium, the conditions for forming complex rocky worlds improved. By the time our solar system formed, the the galaxy had already undergone billions of years of chemical evolution, creating a richer environment for planet formation. The existence of planets much older than Earth shows that this process began earlier than once thought, but it also highlights how unusual Earth may be in some respects, forming in a region with relatively high metallicity and a stable, long-lived star. Another change over billions of years involves the gradual thinning of star-forming gas in certain regions of the galaxy. While new stars continue to form, the overall rate has declined compared to earlier epochs. The Milky Way is still an active galaxy, but it is no longer in the most vigorous phase of its star-forming history. For ancient planets, this means that their surroundings may have become quieter over time. Regions that were once filled with bright, short-lived stars and frequent supernovae may now be populated mainly by older, more stable stars. Imagining such a long progression can create a sense of continuity, a reminder that the galaxy we see today is only a snapshot in an ongoing process that has been unfolding for billions of years and will continue for billions more. When we look at the oldest known planets, we're not just studying individual worlds, we are glimpsing relics of an earlier Milky Way, objects that formed when the galaxy was still young and that have persisted through its long evolution. Numbers like 1 million or 1 billion are easy to say, but they are difficult to feel. When astronomers talk about the age of planets, stars, or the universe itself, they use figures so large that the mind often treats them as abstract labels, rather than durations that could, in principle, be experienced if one had unlimited patience. To understand what it means for a planet to be 12 billion years old, it helps to place that age beside other cosmic timescales and see how they relate to one another. The universe is currently about 13.8 billion years old. That number comes from several independent lines of evidence, including measurements of the expansion of space, observations of the cosmic microwave background, and studies of the oldest stars. These methods all converge on roughly the same figure, giving astronomers confidence that the estimate is close to the true age. If a planet is 12 billion years old, it formed when the universe was less than 2 billion years old. That was a time when galaxies were still assembling, when heavy elements were less abundant, and when the first long-lived stars were settling into stable orbits within growing galactic disks and halos. The Milky Way itself was in an earlier stage of its development, with different patterns of star formation and a different chemical composition. Comparing that to Earth's history highlights the difference in scale. Earth formed about 4.5 billion years ago, which means it is less than 1/3 as old as the universe. Life on Earth appeared relatively early, perhaps within a few hundred million years of the planet's formation, but complex life took billions of years to develop. Humans, as a species, have existed for only a few 100,000 years, and recorded history spans just a few thousand. If the entire history of the universe were compressed into a single calendar year, Earth would form in early September, the first multicellular life would appear in December, and human civilization would occupy only the last few seconds before midnight on December 31st. A planet that formed 12 billion years ago would appear near the beginning of that year, long before the solar system existed. Another way to think about cosmic time is to compare it with the lifetimes of stars. Massive stars, those several times the mass of the Sun, may live only a few million years before exploding as supernovae. Smaller stars like the Sun live for about 10 billion years in their main sequence phase, steadily converting hydrogen into helium in their cores. Even smaller stars, known as red dwarfs, can live for tens or hundreds of billions of years, far longer than the universe has existed so far. This means that some of the oldest planets in the Milky Way may still be orbiting stars that are barely halfway through their lifetimes. From the perspective of such a star, 12 billion years is not the end of the story, but merely a long middle chapter. Planets themselves do not have fixed lifetimes in the way stars do. A planet can, in principle, persist as long as it is not destroyed by collisions, engulfed by its star, or ejected from its system. Some planets may survive long after their stars have evolved into white dwarfs, orbiting stellar remnants for billions or even trillions of years. In this sense, planets can be among the most enduring structures in the universe, outlasting not only individual stars but entire phases of galactic evolution. Looking at the history of the Milky Way, we see that star formation began more than 13 billion years ago, not long after the first galaxies formed. The earliest stars were massive and short-lived, but later generations included smaller, longer-lived stars capable of hosting planetary systems that could endure for immense spans of time. Globular clusters, many of which are more than 12 billion years old, serve as time capsules from those early epochs. The stars within them have remained gravitationally bound for nearly the entire history of the galaxy. Planets within such clusters, if they formed early and survived, share that long history. It is also worth considering the timescale of galactic motion. The Sun takes about 230 million years to complete one orbit around the centre of the Milky Way. Since its formation, the Sun has made roughly 20 such orbits. A planet that is 12 billion years old may have completed more than 50 orbits around the galactic centre, travelling hundreds of thousands of light years through space while remaining bound to its star. These long journeys through the galaxy expose planetary systems to changing environments. They may pass through spiral arms rich in gas and star formation, then move into quieter regions, then encounter new clouds and clusters. Over billions of years, the surroundings of a planetary system can change many times, even if the planet itself remains in a stable orbit around its star. Cosmic time also becomes clearer when we consider the future. The universe is expected to continue expanding for trillions of years. Star formation will gradually decline as gas is used up or dispersed. Many stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Galaxies will slowly change shape through gravitational interactions and mergers. In that immense future, planets that survive may continue orbiting faint stellar remnants, illuminated only by the dim glow of white dwarfs or by distant starlight. Compared to those timescales, even 12 billion years is only an early chapter in the long history of the cosmos. Another useful comparison involves geological timescales on Earth. The oldest rocks on our planet are about 4 billion years old, and the continents themselves have been reshaped repeatedly over time. Plate tectonics recycles the crust, erasing much of the earlier record. On worlds without active geology, surfaces can preserve features far older than anything found on Earth, offering a more direct record of ancient events. Meteorites provide another window into deep time. Some meteorites formed in the early solar system and have remained largely unchanged for more than 4.5 billion years. They are fragments of the original material from which planets formed, preserved in the cold vacuum of space. Ancient planets, especially those with little geological activity, may preserve similar records on a much larger scale. Thinking about time on a cosmic scale can also influence how we view change. Many processes in astronomy are gradual. Stars brighten slowly. Orbits evolve subtly. Galaxies shift and merge over millions and billions of years. These changes are not noticeable in a human lifetime, but over immense spans they transform the universe. Ancient planets are witnesses to these slow transformations. They have orbited their stars through multiple phases of stellar and galactic evolution, experiencing changes that would be impossible to observe directly in shorter-lived systems. Another perspective comes from considering the age of the elements themselves. The atoms that make up planets were forged in stars that lived and died before those planets formed. Some of the atoms in Earth's crust are older than the Sun, having been created in supernovae billions of years earlier. In a very real sense, planets are assembled from material that carries a history stretching back almost to the beginning of the universe. When astronomers measure the ages of stars and planets, they are therefore not only determining when those objects formed, but also tracing the history of matter itself, following it through cycles of star formation, destruction, and renewal. Comparing planetary ages to the age of the universe also highlights how early planet formation began. For many years, scientists believed that planets might be a relatively late development in cosmic history, requiring multiple generations of stars to produce enough heavy elements. Discoveries of very old planets have shown that this process began earlier than expected, meaning that planetary systems may have existed throughout most of the Milky Way's history. This realization expands our understanding of how long environments suitable for planets, and possibly life, may have existed in the galaxy. It suggests that the story of planets is not confined to the last few billion years, but extends back almost to the beginning of the Milky Way itself. Reflecting on these immense spans of time can have a calming effect. It reminds us that the universe operates on a scale far beyond our daily concerns. The slow motion of stars and galaxies, the gradual cooling of planets, and the steady passage of billions of years create a sense of continuity that is both humbling and reassuring. Ancient planets are part of that continuity. They are reminders that the processes shaping the cosmos have been at work for vast stretches of time and will continue long into the future. Looking at planets that have existed for billions of years longer than Earth gives us something rare in astronomy, a kind of natural preview of what very long stretches of planetary evolution can look like. We cannot watch Earth age for 10 or 12 billion years, but we can study worlds that have already travelled much farther along that timeline. In doing so, astronomers gain clues about the processes that may shape our own planet and solar system in the distant future. One of the clearest lessons from ancient planets is that change is inevitable, even when it unfolds very slowly. Planets do not remain exactly as they were when they formed. Their interiors cool, their atmospheres evolve, their surfaces are reshaped, and their stars gradually change in brightness and behaviour. None of these processes happen overnight, but over billions of years their cumulative effects can transform entire worlds. Earth itself is already partway through such a transformation. The Sun is about halfway through its main sequence lifetime, and its brightness has been increasing steadily. When Earth formed, the Sun was dimmer, and the climate of the young planet was very different from what it is today. In another billion years or so, the increasing solar output may make Earth too warm to support oceans on the surface. The planet will not vanish, but it will become a very different place. Ancient planets remind us that this kind of long-term evolution is normal. A habitable world does not remain habitable forever. Habitability is a phase, sometimes a long one, but still a phase within a much longer planetary history. Another lesson concerns the resilience of planetary systems. The discovery of planets that have survived for more than 10 billion years, sometimes in environments far more crowded or turbulent than our solar neighbourhood, shows that planetary orbits can remain stable over immense spans of time. Even dramatic events, such as the death of a star or close encounters with other stars, do not always destroy planetary systems. Some survive, adapting to new conditions. This resilience offers a glimpse of the distant future of the solar system. When the Sun eventually expands into a red giant several billion years from now, the inner planets will be profoundly affected. Mercury and Venus will almost certainly be engulfed. Earth's fate is less certain, but likely severe, with surface conditions becoming uninhabitable long before the Sun reaches its maximum size. Yet the outer planets, Jupiter, Saturn, Uranus, and Neptune, may survive, continuing to orbit the remnant white dwarf that will remain after the Sun sheds its outer layers. In that distant epoch, the solar system will not be gone. It will be transformed, quieter, colder, and very different, but still present. Studying ancient planetary systems helps astronomers understand how such transformations unfold, and how long the remnants of planetary systems can persist. There is also a lesson in the importance of initial conditions. The long-term stability of a planet depends strongly on where it formed, how massive it is, what kind of star it orbits, and how crowded its environment is. Earth has benefited from a relatively stable orbit, a large moon that stabilizes its axial tilt, and a location in a comparatively quiet region of the galaxy. Not all planets are so fortunate, and ancient systems show a wide variety of outcomes, some stable, some chaotic, some reshaped by gravitational interactions over time. Another insight comes from the study of atmospheres. Over billions of years, atmospheres can change dramatically. On Earth, the atmosphere of the early planet contained little oxygen. Oxygen accumulated only after photosynthetic organisms began releasing it, fundamentally altering the chemistry of the air and enabling the evolution of complex life. Later, volcanic activity, biological processes, and interactions with the oceans continued to shape the atmosphere. Ancient planets may have undergone similar or even more dramatic changes, depending on their environments. Some may have lost their atmospheres entirely. Others may have developed thick, dense envelopes of gas. Observing these variations helps scientists understand the range of atmospheric evolution that is possible, and by extension, the potential future of Earth's own atmosphere. The cooling of planetary interiors is another process illuminated by ancient worlds. Earth's internal heat drives plate tectonics, volcanic activity, and the generation of the magnetic field. These processes play important roles in regulating climate and protecting the surface from harmful radiation. Over very long timescales, however, the internal heat of a planet diminishes. Geological activity slows, and magnetic fields may weaken or disappear. Mars provides a nearby example of this process in an early stage. Once geologically active and possibly warmer, it cooled more quickly than Earth because of its smaller size. Its magnetic field faded, its atmosphere thinned, and much of its surface water was lost. An Earth-sized planet would cool more slowly, but given enough time, similar changes may occur. Ancient planets show that such long-term cooling is not just theoretical. It is a natural part of planetary evolution. There's also a broader lesson about the importance of time itself in shaping planetary environments. On Earth, life required billions of years to evolve from simple microorganisms to complex organisms, and eventually to intelligent beings capable of studying the cosmos. Ancient planets, if they remained habitable for comparable or longer periods, might have provided even more time for biological evolution, assuming life arose there at all. This perspective can change how we think about the search for life beyond Earth. Instead of focusing only on planets similar in age to Earth, astronomers also consider much older worlds, where life, if present, would have had vast stretches of time to develop. Ancient planets also offer insight into the future of the Milky Way itself. Over billions of years, the galaxy will continue to evolve. Star formation will gradually decline as gas is consumed. The Milky Way and the Andromeda Galaxy are expected to merge in about 4 to 5 billion years, reshaping both galaxies into a single, larger system. Planetary systems, including our own, will be carried along in this process, orbiting within a new galactic structure. From the perspective of a planet, such a merger will unfold slowly, over hundreds of millions of years. The night sky will change gradually, with new patterns of stars appearing as the galaxies approach and eventually combine. Ancient planets that already existed during earlier mergers in the Milky Way's history may have experienced similar transformations. This long view also highlights how temporary many features of planetary systems are. Rings around planets dissipate. Asteroid belts change as objects collide or are ejected. Comets are gradually depleted or redirected. Even moons can drift slowly outward or inward over time due to tidal interactions. The Earth-Moon system, for example, is slowly evolving. The Moon is moving away from Earth at a rate of a few centimeters per year, and Earth's rotation is gradually slowing. These changes are tiny on human timescales, but over billions of years they become significant. Ancient planets remind us that these slow processes never stop. They continue steadily, shaping the future in ways that may not be obvious in the present. Another lesson comes from the persistence of simple physical laws. Gravity, thermodynamics, and orbital mechanics operate the same way now as they did billions of years ago. The ancient planets we observe today formed under the same basic principles that govern our solar system. This continuity allows astronomers to use present-day observations to infer events that occurred long before Earth existed. In a broader sense, studying ancient planets encourages patience in thinking about the future. Human societies often focus on timescales of years or decades, occasionally centuries. Astronomy, by contrast, deals routinely with millions and billions of years. Seeing the universe through that lens can shift perspective, reminding us that change is constant but often gradual, and that stability, when it occurs, can last far longer than we might expect. The existence of planets older than Earth also underscores the idea that our planet is part of an ongoing story, rather than the final chapter of planetary evolution. There were worlds before Earth formed, and there will be worlds long after Earth has changed beyond recognition. Reflecting on that idea can be both humbling and comforting. It places our planet within a larger context, one in which creation, transformation, and persistence are continuous processes. After spending so much time exploring ancient worlds, immense spans of history, and the slow unfolding of cosmic change, it can feel a little strange to return to the present moment. The room around you is quiet. The sounds near you are familiar. Time here moves in minutes and hours rather than in millions of years. And yet, everything we have been thinking about is still connected to this moment, because the same universe that shaped those ancient planets surrounds us right now. The atoms in the air, the ground beneath you, and even in your own body were formed long before Earth existed. Some were forged in stars that lived and died billions of years ago, perhaps in the same early eras when the oldest planets were forming. In a very real sense, the story of deep time is not something distant or separate. It is part of the story of everything around us. One of the most calming aspects of thinking about cosmic timescales is the realization that the universe moves at its own steady pace. Stars do not hurry, planets do not rush through their orbits, galaxies do not change overnight. Everything unfolds gradually, guided by simple physical laws acting over immense spans of time. It can be reassuring to remember that. In daily life, so much feels urgent. There are schedules, responsibilities, plans, and expectations. But beyond the immediate concerns of any single day, the larger universe continues in its slow, patient way, unchanged by the small fluctuations of human affairs. The oldest planets we have talked about tonight have existed through changes so vast that they are difficult to imagine. They have orbited their stars while galaxies merged, while clusters drifted, while countless generations of stars were born and died. They have endured not because of any special effort, but simply because the laws of physics allowed their orbits to remain stable, their paths continuing year after year, age after age. There is something quietly comforting in that image of steady motion, of persistence without struggle. If you imagine standing on such a world, looking up at a sky filled with unfamiliar stars, the passage of time would feel very different from how it feels here. Seasons might pass if the planet had seasons. The stars would shift slowly over centuries. But most changes would be so gradual that they would hardly be noticed from one generation to the next. That kind of stillness is difficult to experience in our own lives, yet listening to stories about the universe can sometimes create a similar sense of calm, a feeling that there is no need to hurry, that things can unfold at their own pace. Another thought that often arises when considering ancient planets is how much of the universe remains unknown. Even with powerful telescopes and careful observations, we have discovered only a tiny fraction of the planets that exist in the Milky Way. There may be worlds older than any we have found so far, orbiting faint stars or drifting silently through interstellar space, waiting to be discovered in the future. The universe is vast enough that there is always more to learn, more to explore, more to understand. And that sense of openness, of endless possibility, can be gently comforting rather than overwhelming when we allow ourselves to think about it slowly, without urgency. Looking back over what we have explored, It is remarkable how many different ideas connect to the simple question we began with. Asking about the oldest planet in the Milky Way leads naturally to thinking about how planets form, how stars evolve, how galaxies change, and how time itself can be measured on scales far beyond human experience. Each of these ideas is part of a larger picture, one in which everything is connected. Stars create the elements that form planets. Planets orbit stars and evolve over billions of years. Galaxies provide the environments in which stars and planets form, and time, steady and unbroken, links every stage of this process together. Sometimes it helps to imagine the history of the universe not as a sequence of dramatic events, but as a long, continuous flow, like a slow river. There are moments of turbulence, such as supernova explosions or collisions between galaxies, but most of the time the current moves quietly, steadily, carrying everything along. Everything. Ancient planets are like stones resting in that current, shaped by it but also enduring within it, remaining while the water flows past. Thinking about such immense durations can also change how we see our own place in the universe. Human lives are brief compared to the age of planets or stars, yet they are part of the same continuum. Every observation, every discovery, every quiet moment spent looking at the night sky adds to our understanding of the cosmos. And understanding, even in small ways, can bring a sense of connection, a feeling that we're not separate from the universe but participants within it. If you were to step outside on a clear night and look up at the stars, some of the light reaching your eyes would have begun its journey years or even centuries ago. A few of the faint points of light might be stars that formed billions of years in the past, perhaps in the same ancient epochs we have been discussing. Their light travels patiently across space, arriving here long after it began. That quiet persistence, like crossing unimaginable distances without hurry, is another reminder of how differently time can be experienced on cosmic scales. Returning to the idea of ancient planets, it is interesting to consider that some of them may continue to exist long after our own planet has changed beyond recognition. Billions of years from now, the sun will evolve, the solar system will transform, and Earth will no longer be the world it is today. Yet elsewhere in the galaxy, other planets may still be circling their stars, continuing their long journeys through time. This is not a sad thought when viewed from the perspective of astronomy. It is simply part of the natural cycle of the universe, in which new systems form as others change, and the overall story continues without end. There is also something quietly hopeful in knowing that the universe is so vast and long-lived. It means that there is always more time, more space, more possibility than we can easily imagine. Even as individual stars fade and individual planets change, the larger cosmos remains rich with activity and potential. As this gentle exploration comes to a close, it can be helpful to let your attention return gradually to the present. Notice the rhythm of your breathing, steady and unforced. Notice the surface beneath you, supporting you comfortably. The same physical laws that guide the motion of planets also govern the small familiar processes of the body, the steady movement of air in and out, the quiet beat of the heart. There is no need to think about everything at once. The universe is vast, but this moment is simple. Just breathing, just resting, just listening. If your mind drifts back to the images we have considered tonight, ancient planets circling distant stars, crowded globular clusters glowing with countless points of light, the Milky Way slowly changing over billions of years, let those images pass gently, without effort, like clouds moving slowly across a wide sky. And if sleep begins to arrive, that is perfectly fine. The universe will continue its quiet motion whether we are awake or asleep, stars turning, planets orbiting, galaxies drifting through space with unhurried patience. Thank you for spending this time here, exploring these ideas together, letting curiosity and calm move at the same gentle pace. And as the night continues, you can simply rest, knowing that somewhere far beyond the reach of our telescopes, ancient worlds are still moving through the darkness, steady and silent, keeping time in a universe that never needs to hurry.